So hi. A very good morning to everyone, and before I begin, I will like to thank the organizers for inviting me and giving me opportunity to present my work. So this is a recent work I have done in collaboration with my student Hemant, and the topic is simply dark hypercharge symmetry. So this work is about a new class of U1X gauge theories that we have constructed, and they have something to do with dark matter, so dark, and they have some characteristics which are shared with hypercharge of the Standard model. So that's why we call them dark hypercharge symmetry. So let's begin. So this is basically a outline of my talk. So I will give an introduction and then I will discuss anomalies in a Standard model and how hypercharge comes out to be a unique solution. So this will be more to set up the notations and also for students etc. to clearly follow the discussion. Then I will discuss about what are the requirements to add from anomaly point of view, what are the requirements to add a new U1 gauge symmetry to Standard model, and then I will just briefly mention some of the known solutions. Many of them you might have heard about. And then finally I will come to this new class of solutions and then its related phenomenology. So let's begin. So basically, as you all know, this is just a filler slide if you like. You all know that a Standard model is incomplete, although it's highly successful, but there are things which it can't explain, and hence we need some kind of new physics. Now new physics can come in many forms. One of the popular ways to add new gauge symmetries. Now new gauge symmetries can be abelian or non-abelian. I am going to focus mainly on when you add a abelian gauge symmetry. Now these kind of abelian gauge symmetries also occur in many contexts, and in recent time they have become quite popular. So for example, various anomalies like there was this RK star anomaly which is no longer there, or G-2 anomaly, or other kind of phenomena. People have looked at U1X theories as a solution. Okay. Now one of the reasons U1X theories are popular is they are predictive. So compared to other kind of extensions, here the charges of the gauge charges of the Standard model particles and the BSM particles to an extent are fixed by just simply the anomaly cancellation condition. So among all kind of BSM extensions, probably the gauge extensions are the most predictive of the lot. So their predictivity and simplicity makes them very popular. So I'm just going to focus on that, and what I'm going to do is I am look at this problem from the anomaly side of things. So I will ask the question, what are the conditions under which the gauge theory becomes anomaly free? So what are anomalies? Anomalies are basically a phenomena where theory is classically invariant under some symmetry, global symmetry, and when you quantize the theory, you find that the theory is no longer, the quantum theory is no longer respecting that symmetry. Now these anomalies, and I am going to focus mostly on the gauge anomalies, are in gauge theory can be catastrophic. So if they are there, then your theory can become non-rerangeable and all kind of, you lose predictive power. So these gauge anomalies are typically induced by these triangle diagrams. So what are these triangle diagrams? So you have at each vertex you have a gauge boson, whichever gauge theory you are working in, and if your theory has fermions, then they run in the triangle. Now not all gauge theories are anomalous. So for example, if your gauge theory is purely a gauge theory, there is no matter field, no fermions in it, then you don't have to worry about it. But if there are fermions, then you have to worry about it. Also, if your theory is only a non-abelian theory, then the anomalies automatically cancel. However, in Standard model and the theories I am interested in, there is a U1X gauge symmetry. Okay, so there is a U1 symmetry, so you have to worry about anomaly. Okay, so let's first look at how anomalies cancel in Standard model. So standard model is has a abelian gauge symmetry, namely the hypercharge. Its particles, the fermions are also chiral, means the left and right components do not have same charges under SU2 and hypercharge both. So SM can be potentially anomalous. So now to ensure that standard model is not an anomalous theory, what you have to do is you have to ensure that all possible triangle diagrams cancel out some way. And here are the complete set of anomaly cancellation conditions, and Y is basically the hypercharge of the SM fermions. So you can have one anomaly will be when there are two gluons and then the B mu attached to the vertex. So this is this first condition, and this anomaly can be cancelled if the hypercharge of the quarks. So capital Q is quark doublet, I is the generation index, and a small q are the quark singlets, U and D both, and J is the generation index. Okay, so the first condition, if the right hand side is 0, the hypercharges of the quarks are such that they cancel each other, then this anomaly will be cancelled. And similarly for other, the second one is with SU2 times hypercharge. This is the cubic anomaly of hypercharge itself. And finally I have also included what is called the gauge gravity anomaly, because you can solve it also, so why not. And you can see that all these anomaly cancellation conditions require certain constraints on the hypercharge of the SM fermions, or the fermionic particle content of your model. Okay. Also notice one thing, that left-handed particles and right-handed particles come with opposite sign. Okay. So that's a general feature. So if you have vector fermions, means in my notation vector has nothing to do with the gauge bosons. Vector means the left and right fermions have equal charges under the gauge symmetry. Then you can see their contributions will cancel out. So vector fermions do not contribute or change the anomaly cancellation. So you need to have chiral fermions. Standard model has chiral fermions. So you have to solve this anomaly cancellation condition to get the to ensure that standard model is anomaly free. And here is the standard canonical solution that you all have read in the books. So Y is the overall normalization constant, and the charges are like this. So Y by 3, 4Y by 3, minus 2Y by 3, etc. So this is a standard canonical solution, and the choice that people, for any Y the anomalies cancel, but the usual choice is you either take Y equal to 1 or Y equal to half, depending on how you define the relationship between electric charge and hypercharge. So these are the two popular choices. Now you can ask the question, okay, so is this solution unique or not from anomaly cancellation point of view? And the answer is no. There are other solutions. So for example, you can simply flip the charges of the up and down type quark. So you just assign up type quark minus 2Y by 3 and down type quark 4Y by 3, and that's also a solution. You can also find other solutions, and this is for one generation case only. You can also find other solutions, like for example, you can assign hypercharges to these guys as 0, and then you put the anomaly cancellation conditions require this condition. So all these solutions are valid solutions to the anomaly cancellation conditions. But you know, the hypercharge also has another constraint on it, namely that the electroweak theory has to break and EM electromagnetism has to emerge out of it. So there has to be a relationship between the electric charge and the hypercharge. Now for a standard model, guys, this is the relationship, the canonical choice. But you can check quickly that none of these choices give you the correct known electromagnetic charge of the SM fermions. So although these are valid solutions from anomaly cancellation point of view, they can be rejected because they do not give a relationship. And you cannot also change this relationship to have a consistent relationship which gives, for example, for this choice the correct hypercharges, electric charges. So adding this additional requirement makes hypercharge a unique solution, standard model. Now you can ask, okay, this was for one generation, what about 3 generations? So in 3 generations, the canonical choice is that you replicate the hypercharge generation. So here for one generation I had hypercharge is like this. When I have two additional generations, I just make it Qi. Each generation of a particular type has same hypercharge. So it goes generation by generation. And this canonical choice cancels anomalies, of course. Each generation by generation. Now you can ask, are there more solutions? The answer is again yes. Those solutions you can simply replicate generation by generation, they are also solution. You can ask, are there more solutions which are not there in one generation? And again the answer is yes. So for example, these are two solutions. Here what I have done is given hypercharge 0 to all the leptons, and the quarks, two generations have equal and opposite charges, and the third generation has 0 charge. And you can check that this is also a valid solution. Similarly, you can do the opposite, give all the quarks 0 hypercharge and the leptons equal and opposite hypercharge. That's also a valid solution. But again, the same problem comes because hypercharge and electric charge have to be related in some way. None of these solutions you can do that. There is also additional problem that with just standard model Higgs you cannot generate the masses of all the SM fermions for these choices, but that can be solved more easily by adding extra Higgses. So that's also a problem, but that has a solution. But this one, and the relationship between electric charge and hypercharge cannot emerge, and that is a more serious problem. So in conclusion, hypercharge indeed is a unique solution, but the hypercharge of SM fermions cannot be fixed solely by anomaly cancellation condition. You need aggregation requirement. So that's the story of standard model. Now you are planning to add a U1X symmetry. So you have to first ask the question, what are the additional anomalies that you have to worry about? So in addition to those 4 anomalies of standard model, now you have to worry about additional 6 anomalies. The pattern is same. This is color square times new U1X symmetry, SU times U1X symmetry, and now you have 2 U1 symmetries. So hypercharge square times U1X, U1 hypercharge times U1X square, then the cubic and the gravity. And now X is the charge of the fermions. So now I have put a prime over everything because typically anomaly cancellation solutions, as we will see, require addition of fermions beyond the standard model. So now the primes represent any additional fermions of this type. So Q prime means the standard model quark doublets plus any quark doublet you might have to add to cancel anomalies, and similarly for others. So these 6 plus those 4, now you have to cancel 10 conditions. Okay. Now we saw that with 4 conditions, hypercharge emerged out as the unique solution. Now you have 10 conditions. Is there a unique solution? The answer is no, because you remember the anomaly cancellation solution even there was not fixing completely the hypercharge. Here with a U1X, the advantage is, or the liberty is, that now you are not bounded by any relationship between U1X charge and electric charge. Okay, U1X might be related with electric charge, but it need not, unlike hypercharge. So because you do not have that extra condition, there are many solutions. So some of the more famous known solutions I am listing, but this is not an exhaustive list. So these are the Li minus Lj solutions. One of them, L mu minus L tau, became very famous during RK star anomaly era. So what is this solution? It's like a solution I mentioned before for the hypercharge case, but now for U1X. So what you do is, you give all the quarks 0 U1X charge, and then among the 3 generations of leptons, 2 generations have equal and opposite charge, and the third has 0 charge. And if you are just worried about anomaly cancellation, you don't even have to give the right-handed guys same generation, the same charge. You can have 2 different generations having the charge. The only requirement is doublets. 2 generations should have equal and opposite charge. Singlets, 2 generations should have equal and opposite charge. And quarks charges are 0. This is a anomaly free solution. Now also one thing you should notice is this is a vector solution in the sense that the left and right guys have same charges. So I mean, there is a left quark which has X charge, there is a right-handed partner which also has X charge. They differ in generation, but not left-right. Okay, so I am calling this such type of solutions as vector solutions. There are other solutions, for example, B minus L, where you have to add additional fermions to standard model. Typically, they are called right-handed neutrinos. I will just call them F for, okay. So here, the quarks doublets and singlets all have 1/3 charge, and the leptons all have -1 charge. So that's why B minus L. And again, you have to add this new 3, which are typically called right-handed neutrinos, with -1 charge to cancel anomalies. And again, this is a vector solution. Left and right have same charges, so for leptons and quarks both. And there are other possibilities. I have just put some of them here. So now one of the common feature of all these known solutions is that the left and right guys have same charges under the U1x symmetry. But you remember hypercharge. Hypercharge was in that sense different, because if you look at hypercharge, then the left and right guys for each combination have completely different charges. It's a truly chiral symmetry. So you can ask the question, what about chiral solutions to U1x anomaly problem? Are they known? The answer is yes, there are some solutions known in literature where the solutions are chiral in nature. So for example, here for the B minus L case, there is also a known solution where the new guys you have added, you give them exotic charges under the B minus L symmetry. There are also possibilities with other symmetries. However, all these solutions are limited in their chirality, because what you are doing is you are keeping the standard model fermions vector, and whatever new fermions you are adding, you are making them chiral under the U1x. Okay, and there is a good reason why people do that, because if you make the standard model fermions chiral, then you will have problem with mass generation, because the Yukawa term will no longer be invariant under the U1x symmetry. So people prefer to keep the standard model part intact, and whatever chirality you want to introduce, you introduce in the new fermions. So we wanted to ask the question that so these are limited chiral, not like hypercharge. So are there chiral solutions which are completely chiral, just like hypercharge? And the answer is yes, that's why I'm giving the talk. So there is a whole class of solutions which are known, not known in literature, which are truly chiral, like hypercharge. So these solutions we are calling dark hypercharge solutions, and the new fermions that you have to add, and again we will restrict ourselves to 3 fermions only, just like B minus L. They actually belong to a dark sector. The lightest of them will become stable, and then this Z prime will mediate interaction between the visible and the dark sector. Okay. So here you can do it for 3 cases. All 3 generations are chiral. R3 generations are charged under the U1x symmetry. 2 generations are charged. Only 1 generation is charged. So here are the possible solutions when all 3 generations are charged under the U1x symmetry. Same generation by generation, it's same. So you can see, if I put k equal to 0, this is a hypercharged solution. Okay, but k need not be 0, but this is sort of a trivial solution. Other solutions are highly non-trivial, and as you can see, x and s and kappa are all free parameters. So these are truly chiral solutions. In none of these solutions, left and right have same charges. Standard model as well as. And we have also put an additional requirement that the masses of the standard model fermions are generated simply by the Higgs. So just the Higgs Yukawa, yes. Sorry? So I am calling them F. You can identify them with right-handed neutrinos. There are 3 additional fermions, which are SM singlets, only charged under U1x. You can call them right-handed neutrino, but I am going to identify them with dark sector. So they need not be right-handed neutrinos. So they are truly chiral in their nature, and also we have demanded that all SM fermion masses are generated by just the Higgs. So there are constraints on the charge of the SM Higgs as well. How much time? 0. Okay, so I will rush. So then there are also solutions where only 2 generations are charged or 1 generation is charged. And now, as I said, the new guys I have added belong to the dark sector, so the lightest of them automatically becomes stable. So here's the phenomenology part. So basically there is a new gauge boson. So this is the neutral gauge boson mass matrix. One of the eigenstate you want to identify with photon, which will be the massless one, and the 2 massive ones. One of them you will want to identify with Z, and the other one is Z prime. So here we looked at the Z prime being heavier than Z limit, in which the lighter one is Z and the heavier one is Z prime, the mixing angle between Z and Z prime naturally goes to 0 as the mass of Z prime goes to large. So there is an automatic decoupling, unlike say kinetic mixing models. And rho parameter also you can satisfy. So we did all these checks, and since I am running out of time, I will rush through. So then for rest of the phenomenology, we took a definite value of charges just to be definite. So now these guys can be, the Z prime can be produced in colliders via the Drell-Yan process, and its production cross section is higher than say B minus L. So these dashed lines are the B minus L for two different choices of coupling. The solid lines are the hypercharge case. And then because the charges to these invisible guys, the dark sector guys, are large compared to the standard model, so this is a unique feature. You have large invisible decay widths. So almost 90% of the Z prime goes to invisible. Now you will think that because it goes 90% to invisible compared to let's say 38% for B minus L, you can hide this Z prime boson, but remember its production cross section is also large because it has large charges under the, so it will be promptly produced. It will decay mostly invisible, but still the limits are not so different from the B minus L case. So the solid lines are our model when it goes to invisible, when it doesn't go to invisible, and these are the B minus L cases. So although it goes largely to invisible, it is not completely, hidden. So it's promptly produced, you can detect it. And then finally, this is the dark matter phenomenology. The crux, I will just say, is that there is a parameter space where the fermion satisfies the Rayleigh abundance correctly. All these parameter spaces are ruled out by different constraints. And being a two-component fermion, it has very low direct detection because only spin dependent one is available, so it satisfies all the constraints. So the fermion, the lightest of them, is a good dark matter candidate. So I will just stop here, out of time.
So that's time for excellent talk. Are there questions, comments?
You mentioned, but I wanted to understand why is it that the ZZ prime mixing goes to 0 at large MZ prime?
So I do not have the mixing formula, but this is unlike the kinetic mixing. So we have assumed the kinetic mixing to be 0 or small. If there is kinetic mixing which is possible, then that will not happen. But basically, so I do not have exactly the formula for the mixing angle, but mixing angle is inversely proportional to the mass of the Z prime. So it just goes to 0 as Z prime becomes heavy. So the Z and Z prime decouples, kind of.
Are there other questions? Okay, if not, we can talk to Rahul offline. So let's thank Rahul again for the nice talk and also for all the other speakers in the panel discussion.